Alright, let's solve the Leetcode problem. So the Leetcode problem is the maximum level sum of a binary tree. So by reading the question, I'm pretty sure that is the tree problem. Probably when you can solve it with the depth search or breadth search. So given the root of the binary tree, the level of its root is 1, the level of its children is 2, and so on. So that means we are counting the level of the root with the starting with the number 0, not like the 0 bits index array. And then we have to return the smaller level such that the sum of all values of nodes at x is maxima. Okay, we just need to return the binary tree level where the summarization of all the values on that node level is the maximax. So okay, let's try to go through the examples in here. So let's consider like we are given like an array, which is the rows, but I'm pretty sure in the given question, we are not receiving array. We are receiving with a custom data type like a tree or node data structures. And then since it is given an array as an example in here, so 1 is here and 7, 0 is left and right. And then at the same time, 7 minus 8, which are the subchild of the 1. So there's no item at the children of the 0, so it's becomes non-null. So by calculation that, by summarization of the each level, so this is a level 1. We need to write that as a level, if not it will be confused. And then the same for the here. We have a summarization that's called sum in here. So for this row, the summarization is since only the one number is 1. So for the second row, that is a 7. But for the third row, that is 7 plus minus 8, which is going to be the minus 1. So according to this, our answer is pretty straightforward and clear. We just need to return the 2. But it's not that much simple when we try to write the code. So yeah. And then let's try to give it a shot for the example 2. Maybe I will move this along to our right side of my preparation. So we are given like 989, 10,250, 98,693 minus 89,399 minus 32,000 and minus 127. So there's no reasons we should consider this since it is a huge negative integers in here. So by writing the label here 1, 2, 3, so 9,305 is the summarization between the 98,693 and 89,388. So at least they got the positive integer 9,305, and then the second number is 10,250, and then for the first row that is 989. So the awards and the answers go to level 2. That's why the output is 2 in here. So to write the code, my approach is using the stack approach. So what I mean by stack approach is we need to check the constraint first before we start writing it. Since the number of nodes in the tree is a minimum 1, so we don't need to consider like we are making something wrong in here, or we need to have an edge case or base case. Let's consider that we use the queue. Yeah, just call it as a queue, even though we're using the stack data structure. And then what I want to use is a tree node, which is a custom data structure, which is declared above and described in here. And then our initial value will be root. So that means we put in the optional values in the non-optional data type. Since the tree node itself is we're not marking as optional, but the root data type is an optional. And I think we need one base case in here since we don't want to see the optional case in here. Let's consider like root plus return just call 0, but that case will never happen. the reason why that giveaway never happened is we were pretty sure to have a integer value for ones in here in the range. So moving forward, we need to keep track of the level, which will be the 1 initially, and then I want to keep track of the reset level, which will be the, so initially that is a 1, and then I'm gonna iteration through like if until the queue is empty. So originally it would be false, so we gonna make it like reverse operator, and then we will check like what could be the possibility if we want to iteration through. So the first thing I want to do is we want to count like q dot count. So the reason to count itself is like if we have a count for the queue, we get iteration from 0 to the end of the array. So even though we're calling the label 1, 2, and 3 in here, at the end behind the since the array is using 0 index array. So let's call like we need a one sum variable in here. So we're gonna keep track of the each row sum values, what is the maximum sum value or not. So by checking that, what I want to do is how about we iteration through from the, actually we need index or not, 0 through count. So in our case, there's only one item at the first, so it's like this. So at least our item will iteration for once a while, since we only have initial basically of the one roof item in the array. And then moving forward, what I want to do is I want to update the nodes by removing the first item. Let's call it like remove first. So this is going to pop it up, and then we will make the queue begin the empties in here. So I have a valid reason to remove the first in the line method D. The reason is I'm going to calculate like sum as a node dot value. So we have a values in here, which is a valuation like 1 in here. And then what I want to do is if we have left item, let's call left, I want to append to the queue. That is the reason why I'm telling you since the beginning how about we use a stack data structure. Now we are really using it. And then I'm gonna append the left to our queues in here. If there will be another case, what if we have a right child? We're gonna append that also. So moving forward, since we don't have like any item efforts, and then our queue is no longer empty, it's become the 2, and then we have 2 items here, something like left and right. So if we have a left and right, what we can do in here is it will iteration through easily, but we need to have a format base case in here. Every time we have done for the iteration approach for the summarization of the each row of the binary tree, what I want to do is I'm going to check like if our sum value, we need the one variable in here to keep track of the best sum. Let's call like best sum, maybe initially the minimum number of the integer, and then we're gonna compare like which one is the largest cross between our original sum and the best sum. So if the sum is larger, we're gonna update the best sum where we begin the sum, and then we also need to update the best level. It's going to begin the level. After that, we're gonna iteration of the level with the +1. If everything worked well, we just need to return not the best level. That's a weird naming. How come I confuse it? Okay. Yep. We have a result level updating here, and then I just return the result level in here. Let's see if solve the problem or not. Yep, I think that is the O(n) approach, since we don't have like recursive or traverse in here, since we are just using a queue and some kind of like stack data structure. I think for the memory wise, that is the O(w). That's weird. So W came from the width of the tree, I would say. Okay, width and height. So I need to measure like this. So if I measure by height, so it's something that we calculate from top to down. But now it's mentioned like width is here, like we go from left to right. So as long as we have a bold subchine and chine in our binary tree, our solution will be going to take longer memories in here. Yep. I think that's all for it, and let's see you in the next one. Thanks.